Hello, and thank you for attending this presentation at the Eurosteel 2020 conference. I'm Charles Gillott, a PhD student from the University of Sheffield, and today I'll be presenting a small element of my work on sustainable housing provision, making the case for and discussing the potential of the vertical extension of existing steel frame buildings. This work sits at the overlap of two crises that we face today, that of the global climate crisis and also the growing housing crisis that we currently experience here in the UK. Amongst other factors, under-provision of housing is one contributor to the soaring house prices and near record levels of homelessness now seen in the UK. This has meant that over 280,000 people are now estimated to be homeless in England, making that 1 in every 200 people on average. Growing house prices result that the average cost of a first-time home is now almost £200,000, meaning that vast portions of society are simply priced out of home ownership on a scale that has never been seen in this country before. In response to this, the general consensus of estimations from governmental and non-governmental organisations is that somewhere between 250,000 and 380,000 new homes must be generated per year just to keep up with demand. Considering that only half this amount were built in 2019, this represents a formidable task for the UK construction sector. Adding to the complexity of providing such large quantities of housing is the fact that this must now be done in the midst of a global climate crisis. The current state of play means that we're on track for about a 3 to 4 degree increase in global average temperatures by the end of the century. In order to avoid the catastrophic changes to our climate that this would result in, we must limit this to just 1.5 degrees, in line with the recommendations of the Paris Agreement. To meet this 1.5 degree target, there is a requirement for global greenhouse gas emissions to reach net zero by 2050. With buildings being responsible for almost 40% of greenhouse gas emissions, it is therefore the case that every possible effort should be made to decarbonise the construction industry as quickly as possible. One of the ways in which this may be achieved is through prioritising the adaptive reuse of existing buildings over demolition and reconstruction, something which has vast embodied carbon benefits. This is because avoiding demolition generates less waste, and because less material and energy is consumed in adapting a building than in building something comparable from scratch. In the context of housing provision, where the generation of new usable floor space is the main focus, vertical extension is one of the most relevant ways in which existing buildings can be adapted. This also means that housing is able to be provided without the negative effects of urban sprawl or the consumption of undeveloped land within cities. In turn, as the cost of land contributes greatly to the expense of traditional housing provision, this also means that vertical extension can generate housing that is more affordable. Housing more people within the footprint of existing buildings also serves to increase the residential density of an area, providing additional environmental and socio-economic benefits. These benefits have been recognised by the government in an acknowledgement of the role that vertical extension has to play in future housing provision. This has meant that changes to planning laws have recently been made to allow for the delivery of accommodation through vertical extension without the requirement for a full plan application. When considering which building archetypes may be particularly suitable for vertical extension at the outset of this work, it was quickly revealed from existing literature that multi-storey steel frame buildings are where focus should be placed initially. This is because they are relatively abundant, occupying an annual share of more than 40% of the non-residential multi-storey frame market for the last 35 years. Combined with the relative durability of steel in comparison with alternatives such as concrete, this means that multi-storey steel frame structures make up a significant portion of the UK's current building stock. The inherent durability of steel also means that the design life of existing steel frame buildings may be easily justified beyond its initial intended duration. On top of this, steel buildings also tend to be more easily adapted than concrete or masonry alternatives, making structural remediation and strengthening easier where it is required. We also know from existing work that steel frame buildings are likely to possess reserve structural capacity that may be utilised in a vertical extension, with one study revealing that the columns in 23 case study buildings were utilised by less than 50% on average. It should also be noted here that steel has a role to play in the construction of rooftop extensions themselves, with cold-formed steel structures often being used to provide a lightweight and relatively low embodied carbon solution. Logically, the potential success of housing provision through vertical extension depends somewhat on the presence of reserve capacity within existing buildings. The issue here is that, although the sources of reserve capacity are well documented, the amount contributed by each has rarely been investigated. The aforementioned study by Moynihan and Allwood suggested that rationalisation was the major cause of this, resulting in a small number of section sizes being used in different loading cases for ease of procurement and construction. The limited number of section sizes available for selection also worsens the effect of this, and means that all steel elements are inherently over-designed by at least some margin. Advancements in steel production and improvements in the accuracy of design codes also mean that significant amounts of reserve capacity may be identified in slightly older steel frame structures, should they be reappraised using modern codes of practice or tested material strengths. The conservativity of assumed live loads in current design codes also means that there might be further reserve capacity in some structures, should these be revised in the future. One example of this is the fact that the assumed loading for office buildings has remained at 2.5 kilonewtons per metre squared in Eurocodes, despite dramatic changes to how we use offices, meaning that actual experience loads are found to be somewhere closer to 1.5 kilonewtons per metre squared. Some engineers also have a historic and continued preference to use analytic design methods. This means that reserve capacity may be found should existing buildings be reappraised using more modern or upgraded analyses. It is a possibility for this that is investigated by this piece of work, which investigates the effect that considering column continuity has on the buckling capacity of multi-storey columns. Often, multi-storey columns are sized using the effective length method, which results in them being modelled as a series of individual pin-ended columns. As such, their effective length is taken as equal to the inter-storey height. This is evidently incorrect, however, with the column portions adjoining the critical section actually serving to add additional rotational restraint, as shown here. This decreases the column's effective length, therefore increasing its buckling capacity. To overcome this, successive adaptations by Gantes and Majerus in 2005 and Weber et al. In 2015 have resulted in a set of improved stiffness distribution factors. These are capable of more accurately estimating the buckling capacities of columns, with these being in close agreement with the values computed by finite element analyses. The work presented in the subsequent slides of this presentation uses these adaptations to investigate how much reserve buckling capacity is present in multi-storey steel-framed columns. To allow for this, a conceptual non-sway steel frame arrangement was adopted, whereby 3-storey continuous columns are loaded about both axes by nominally pinned beams. This removed the requirement to consider failure about the primary axis and meant that actual and nominal bending moments were not required to be considered. The combined action effect of this frame was assumed to be 11 kilonewtons per metre squared at each floor level, with this value being generated assuming typical office construction and recommended imposed loading. Both column spacing S and storey height H were varied sequentially between limits reasonably expected to be found in office buildings. In this process, one parameter was varied whilst the other remained fixed. For each structural grid configuration, the design force within the critical column section was determined using the assumed loading and attributed floor area. The lightest universal column section capable of resisting this load was then selected using the process outlined in Eurocodes to be representative of a typical design process. This was implemented in MATLAB for computational ease. The frame configuration employing this section was then reanalyzed using the effective length adaptations previously discussed to obtain its improved buckling capacity when considering the column's multi-storey continuity. By subtracting the buckling capacity required by the present design scenario from this value, the reserve capacity present within the column was identified. This was found to result both from the consideration of column continuity, but also because of the limited number of UC section sizes that were available for selection. These are disaggregated here, showing the relative portions of reserve buckling capacity resulting from section size limitations and the neglect of column continuity. This chart shows how reserve capacity varies for increasing column spacing, with the interstory height being fixed throughout. As can be seen from the cyclic nature of the total reserve structural capacity, as column spacing is increased, reserve buckling capacity gradually decreases before immediately jumping up to begin decreasing again. Each of these clusters therefore represents a single section size, with the utilisation of the column increasing as the design scenario becomes more onerous until the next largest section size is required and a new cluster begins. Focusing only on the effect of column continuity, it is revealed that this generally decreases slightly within each cluster, though it does average out at around 1.1 kilonewtons per metre squared. Rather than being a function of the present design scenario, this is instead more likely to result from the reporting of reserve capacity in a per metre squared unit. This is because, as column spacing increases, so does the area over which the reserve capacity is distributed. This in turn results that the uniformly distributed capacity decreases despite absolute booking capacities being much more consistent. A similar cyclic pattern is also seen when story height is varied whilst column spacing remains fixed. This means that if we look at the effects of column continuity and isolation, we see these to be more consistent within each cluster than on the previous slide. This is because the area over which reserve capacity is distributed remains fixed as story height is varied. Despite this, the average reserve capacity identified through the consideration of column continuity for varying story heights is revealed to be 1.4 kilonewtons per metre squared, similar to in the case of varying column spacing. This figure also exemplifies how dramatically the selection of section sizes contributes to reserve capacity, demonstrating the issues associated with rationalisation. It should be noted here, however, that as only UC sections were used in this analysis, the effects of this are exaggerated. This work has assisted in confirming the notion that steel frame buildings are likely to be particularly suitable for vertical extension. This is by acting as an initial pilot project to test the process of identifying reserve capacity through the reanalysis of structures using more rigorous methodologies than was employed in their design. Through the adoption of conceptual frame configurations, this work also reveals that considering column continuity alone does not identify sufficient reserve capacity to allow for vertical extension. Despite this, however, it does contribute a fairly consistent capacity of over 1 kilonewton per metre squared for the frame configurations that were considered. It is therefore likely that when combined with capacity from additional sources or structural remediation, a large portion of the UK's existing steel frame building stock will be readily extendable. One of these sources is revealed to be the limited number of section sizes available for selection, something which also worsens as rationalisation is carried out by design engineers. Despite serving as an initial feasibility study, this work is highly conceptual in nature and only considers the booking capacity of a limited number of frame configurations. Further work is therefore required to identify the total reserve capacity in real-world structures, considering all different possible failure modes. Thank you for taking the time to watch this presentation. If you have any questions on this work or my wider research, please do not hesitate to ask these in the opportunities provided or by contacting me using any of the channels below. Thank you very much.